This is Gyroscopic Precession, Part 3. At the end of Part 2, I said that we would use calculus to derive these two equations. So let's just let this ring that we already have drawn, let's let it be a representative ring that we will integrate from 0 out to the radius of a disk. So let's say this is our disk out here. Okay. Yeah, well, not too pretty a disk. But anyway, let's say the radius of the disk is capital R, and the radius of our ring that we're going to use to integrate, we'll call it lowercase r. Okay. Let's say our incremental ring has the same width as our disk. From there, measured across to there, that distance. Yeah, here's a cheesecake cooking ring. We'll use it to better illustrate this. What we're talking about, width, is from there to there. Okay, we'll call it W. Okay. The thickness of this ring, which is the outside radius minus the inside radius. Yeah, again, we'll borrow the cooking ring. What we're talking about is the outside radius from out there to the center minus from there to the center. In other words, the thickness, which isn't much there. When you're talking about calculus, that thickness is just barely above 0, as close to 0 as you can get. So we'll let that be called dr. Okay. Because we always use d in front of something to indicate a little teeny weeny amount of. And radius is lowercase r, so from there to there would be dr. Okay. The area of this ring is equal to the circumference of the ring, which is, remember the formula for circumference, 2 times pi times r, or pi times the diameter. So circumference, circumference equals 2 pi r. And we said the area of this ring is equal to the circumference of the ring times the width of the ring, which is W. So throw our W in there. Well, circumference equals that. Area equals circumference times W. We'll call that dA. Let's see. Actually, that should be A. Let's see. Okay, the volume of this ring is equal to the area times the thickness. And the thickness, let's see. Yeah, the thickness is dr. So let's just stick a dr on the end there. We'll change this from A to V. Actually, we should make that a little dV because this is a increment of volume. It's a little teeny amount of volume because dr, it involves dr. And dr is next to 0 in calculus. So our little teeny weeny increment of volume is equal to the circumference times the width times the thickness. Our circumference around there times our width from there to there times our thickness from there to there. That's our volume, dV, of this ring. Okay, the mass of this ring is equal to the volume of the ring times the density. So, okay, like if you have a cubic meter, well, that would be volume. And if you have 1 kilogram per cubic meter, or better yet, 1.225 kilograms per cubic meter, that's the density of air at standard temperature and pressure. So if you had a volume of 1 meter times a density of 1.225 kilograms per cubic meter, well, then you would have 1.225 kilograms, which is mass. That's an illustration of how mass equals volume times density. So let's just multiply this by density, which is our letter. It looks kind of like a P. They call it rho in Greek. But since we multiplied it by density, we have to multiply our dV by density. And volume times density is mass. So we'll just change this to dm. So our little increment of mass is equal to all of that. Okay. 2 pi r w rho times dr. Alrighty. Okay, now remember that di equals dm times r squared. Got that written right there. Okay, which means di equals, well, there's what dm is. So if di equals that times r squared, let's just multiply all this by r squared. Multiply that by r squared and we change it into di. Okay, our little teeny weeny increment of moment of inertia equals that. Okay, rearranging the terms, getting all these r's together. There's an r squared. We'll have, let's see, di equals 2 pi times width times density times r squared is r cubed dr. Okay, now we integrate each side of this equation. It's always easy to integrate d something because the integral of di is just plain old I. I equals all these constants here, 2 pi w rho. But when we get to the r cubed dr, integral of r cubed dr is r to the 4th over 4. Okay. Now our limits of integration for a disk are from r equals 0 to r equals capital R there. So let's put our limits of integration here, 0 to capital R. Okay, our limits of integration for a ring are from r equals Ri. So let's write moment of inertia for a ring. Go ahead and write ring there. Go ahead and write disk here. Okay. The moment of inertia for a ring is going to be the same equation, 2 pi width density r to the 4th over 4, but integrated from r inside to r outside. In other words, integrated from this distance to there to this distance to there. In other words, the only difference between Ri and Ro is the thickness of our ring. Alrighty. So our moment of inertia for a ring is, it's that. Let's say we have a ring and a disk. Okay. Let's say the outside radius of the ring is equal to the radius of the disk. We'll go ahead and say this. Let's see. Ooh, I better draw you another picture. Let's take a break. Let's say we have a ring and a disk. This is our ring, this is our disk. This ring's kind of like this ring, nothing in the middle. This disc is kind of like this, something in the middle. Of course, it's not empty like this empty pie pan is. It'd be sort of like being full of cheesecake. Okay, solid all throughout it. Okay, let's say the outside radius of the ring. Here's our ring. Our inside radius is from the center to right there. Our outside radius is from the center to there. Okay, so let's say the outside radius, we'll call it R with a little o standing for outside, is equal to the radius of the disc. So we'll use that same R with a little o to equal the radius of the disc. Okay, the width of the ring from there to there, that width from there to there, is equal to the width of the disc from there to there. And the density of the ring material is equal to the density of the disc material. Let's say the thickness of the ring is very thin. Okay, a very thin ring there. But since we can't use the term very thin in a mathematical equation, let's just say inside radius right there, distance from the center to there. Let's say it's 0.999 times the outside radius. So there's not a whole lot of difference between the inside radius and the outside radius. It's a real thin ring. In other words, thickness of the ring is only 1/1000th of the radius of the ring. The moment of inertia of the ring, I is the letter used for moment of inertia. We just had this equation a while ago. We integrated to get it, and we plug in RO in the first part of the equation and RI on the second part of the equation. 2 pi times the width times the density times the outside radius to the 4th power over 4 minus the same string of stuff, 2 pi times the width times the density times the inside radius to the 4th over 4. And since the inside radius is equal to 0.999 times the outside radius, we'll say I equals 2 pi times W times density times, well, this is the same as that one. This one is the same as that one, except for we replaced RI with what it is in terms of RO, 0.999 outside radius, and all that to the 4th. So what we have is we have 1 to the 4th power minus 0.999 to the 4th power. Okay, 0.999 to the 4th power equals that, 0.99600, blah, blah, blah. So we put a negative sign in front of that, add 1 to it, and we get 0.00399. So our moment of inertia for our ring is this string of stuff times that little number that we're left over with, and we put that to the 4th power and subtract it from 1. And let's see, we're about out of time with this video. We'll take up in part 4.